And it is my great pleasure to have Rob Jackson here today. He's comes from Stanford School of Earth Sciences. He's only been there for a few months. He was at Duke for 15 or 16 years before that, and at the University of Texas before that. And Rob's a good friend and a mentor to me. I was in his lab when I was a postdoc, and I guess we're a little less formal here than we were earlier today. But my first experience with Rob was a fun one where where I joined his lab. He had been working on issues related to plants and root depths, and he had taken a pretty novel approach to it, in that he was studying plant roots by caving, and he called this extreme ecology, and I was so excited to join the lab. And the first time I walked into his office at the University of Texas, I looked at the door, and instead of it saying Robert Jackson, it said Rabid Jackson, because he had an experience in the cave, and he's maybe one of the few people you'll ever hear from who has gone through the whole rabies treatment. And so Rob has had a very diverse career. He started out as a chemical engineer with a degree in chemical engineering from Rice. He then transitioned fairly abruptly into plant physiology, physiological ecology, and his career has been one that's really been marked by anticipating what the world needed to know from science and being on the forefront of research. He was one of the first people studying ecological responses to rising atmospheric CO2, but then he has transitioned recently into issues related to groundwater quality and fracking, and he continues to contribute in meaningful ways to the development of public policy, being a science advisor on issues related to climate change, to atmospheric CO2, to methane emission, and others. He co-chaired the U.S. Carbon Cycle Plan, and he's currently co-chairing the Global Carbon Project, which tracks fossil fuel emissions around the world. And we're just absolutely thrilled to have him here. And so help me welcome Rob to the seminar.
So first of all, thank you everyone for coming. So we don't need the mic for this room, but for people who want me to wear a mic, is it okay, volume-wise? Yeah, I know you guys, because you can hear me. But all right, well, whatever. Thanks for being here. So I didn't bring that story up, but I have to finish it because he brought it up. It tells you about something about how reverent my lab is. So we actually were caving. We were about 100 feet underground. It was about midnight, and we were scrambling over this rock. I put my hand on this rock, and there was a bat there. And this bat scratches me, and one of the technicians in our lab, Susan Rainey, we start walking on. She says, Rob, you ought to take that bat. And I said, what do you mean, I ought to take that bat? She said, I mean, you ought to take that back and have it that bat and have it tested. And so I did it. I was going to DC the next day. I dropped the bat off at the doctor's office. At DC, I get the call that the bat is rabid. And when I've come back to my lab, when I've come back to my office, my grad students and postdocs have changed the nameplate on my office from Robert Jackson to Rabid Jackson. So that's true. That's where that came from. That's irrelevant to our topic today, but there you are. I want to talk today. I spoke this morning, a little different context, more this morning of a research kind of seminar on hydraulic fracturing and water and air issues and some of the benefits and some of the potential environmental issues associated with it. Today is less of a kind of a research talk and more of a talk about emissions, a little bit about climate change, and it's setting the stage a bit for the series that you are having. It looks like a great series looking at the flyer here. I'm going to put my Global Carbon Project hat on, and Rick mentioned that briefly. The Global Carbon Project is an international group of scientists, and our primary job is to track fossil fuel emissions around the country, so around the world, to compile information on particularly carbon dioxide, but now increasingly methane as well, to provide an annual budget about the emissions and releases of those gases, and then also to track where the gases go, how much of them stay in the atmosphere, how much go into the oceans, how much go on into the land and such, into land sinks. So that's a little bit what I'll talk about today, and this is an informal setting. I'd be quite happy to have a discussion as we go along, and so if you have questions as we go along, please just chime in, and So we'll go through a few examples. The title is Climate Change and Cumulative Greenhouse Gas Emissions, and it's really the greenhouse gas side that we're going to focus on today. So we'll look at the trajectories of emissions, where those emissions are coming from, and what we might say about the future on them. So this is a couple of ancient history pictures. The one on the left was a Time magazine cover from 1987. That was sort of 2 years after the ozone hole had been discovered. So the notion of global warming was already quite discussed at that time. And then this is my favorite news magazine, The Economist, sort of a different perspective, staying cool about our changing climate. That's from 1995. So these are all 20 going on 30 years now. So this has been in the news for a long time. It's a little bit about what I talked about this morning, but in addition to this organizational efforts, I do greenhouse gas emissions work myself. So these are some examples of work that we've done upstream, looking at methane emissions from oil and gas well pads. Downstream, we've produced the first publicly available maps of natural gas leaks in cities like Boston, Washington, D.C. So we've driven block by block across cities like that, literally, and produced maps of thousands of natural gas leaks and where they are, and try to understand what causes them, old infrastructure in particular. So I'm really interested in providing information that helps us learn something scientifically, but also can be useful to improve things. But I won't really be talking about emissions in that narrow sense today. If you'll indulge me, let me take 5 or 10 minutes. Let's talk about climate change. I know you've all seen this sort of thing before, but just a few slides and then we'll get to the emissions side. So what is the greenhouse effect as we set the stage for your series on climate change? Well, obviously it's an effect where the shortwave radiation from the sun comes down to the earth. Some of it's reflected back by clouds. Some of it's absorbed by things in the atmosphere, but it reaches the surface. It's then re-radiated, some of it as long-wave radiation based on the temperature of that surface. And that long-wave radiation makes its passage back out into space. But some of that long-wave radiation is captured or delayed in its passage, if you will, because of the molecules that are in the atmosphere. And the most prevalent molecule is water. But the trace molecules that are affected by, particularly by human activities, are things like carbon dioxide, methane, nitrous oxide, and such. And CFCs are strong greenhouse gases too. All right. Well, that's a kind of a cartoonish approach, but I do want to emphasize the history of this. So, in spite of some of the controversies you may hear about and some of what you know, it's important to understand that over 100 years ago, the basic physics was pretty well worked out on greenhouse gases. Not all the details, not global circulation models and all that, but just the fundamental relationship between these particular kinds of molecules and the Earth's temperature. So going back to the 1820s, Jean-Baptiste Fourier was the first person to describe how the atmosphere traps infrared radiation. He used the greenhouse as an analogy. It's the same Fourier, if some of you remember from math class, you do a Fourier transform. Same guy. 1890s, two people independently made the link between greenhouse gas emissions and the Earth's temperature. So P.C. Chamberlain in England, Arrhenius, you know Arrhenius, he was a Nobel Prize winner for chemistry for other research that he did. Okay, so in the 1890s, people had already made this connection that if we continue to burn fossil fuels, continue to release greenhouse gases into the atmosphere, the Earth would warm as a consequence. All right? They did not say that, they did not view that as a particularly precarious thing. There wasn't really a connection with the environment, but they understood the basic physics of how the Earth worked. Then, of course, Dave Keeling came along in 1958 at the direction of Roger Revelle, and he put the first continuous long-term instrument to monitor CO2 in place, and he did it in a volcano in Hawaii to be high in the atmosphere, to be far away from any sort of industrial activity, to be in the middle of the ocean, and that's the famous CO2 trace that you've all seen before here. So this is the Mauna Loa trace that he started going back to the late 1950s on the left. Here we are now, 2014 today. We're about to top 400 parts per million for the first time on average. On a point basis, we've already done that now. So it's been rising steadily since he began his measurements. And this oscillation, as you know, is the biosphere breathing, if you will, particularly in the northern hemisphere in summer, the photosynthesis that draws carbon dioxide down out of the atmosphere. And then in wintertime, when the plants aren't photosynthesizing and are respiring, that CO2 concentration goes back up. All right. All right, how about temperatures? Well, this isn't a talk where we're going to go through the paleo record relationships between greenhouse gases and temperature and such. You'll get that from other people. But this is just a figure of temperatures going back from 1880, in this case, I think, to 2012 or 2013. So overall, the global mean temperature has increased by 1.5 degrees Fahrenheit during that time period. Hasn't done it equally. You've seen periods of increase here, periods of relative stasis, increase here, a plateau here, probably due to particulate air pollution, among other things. Steady increase going back to the 1970s, flattening over the last decade or so that's gotten a lot of attention. Not totally understood why that is. Some recent suggestions that those are smaller, perhaps smaller scale volcanoes, but especially that there's more heat that's being stored in the deep ocean. So the suggestion is that this may last a decade or so, perhaps a little longer, but that eventually it will continue to go up. We also have not had a strong El Nino of this in this interval, and some of these really strong striking peaks, 1998 in particular was one that was just a radically warm year, and now every year is what used to be radically warm. So even with this flattening off, the most recent decade is by far the warmest decade that we've had in this instrument record, at least. Okay, just a couple of examples. So what about the physical world? What does the physical world tell us? And is the Earth warming, and how would we know? Well, here's a picture some of you may have seen before. This is this was really based on an Arctic report that came out in 2004, 2005. It was a big synthesis of changes that were happening at the Earth's surface up in the Arctic. This 1979 is a baseline year, not because it was particularly special, but because it was the first year that a satellite was launched that allowed these images to be taken. So you're looking at the North Pole, obviously, Alaska. There's Greenland. There's Russia and Siberia. Here's the ice pack in September. Why September? Well, that's the point in time when the ice pack has when the ice has sort of melted back the most. So that's the smallest point, and then it grows back out again, of course, in wintertime. So this is what it looked like in 1979. This is what it looked like at about the time or right after the report came out. So you see a couple of really different things, right? So interesting geopolitically, you can now, at least in this interval, sail a ship from Europe to Japan and don't have to go through the Panama Canal or around the Cape. But you see the decrease in size here compared to this at the same interval, the same period. And in this report, these scientists suggested that the Earth might be ice-free at the North Pole in summer, perhaps in 100 years or 150 years because of the increased temperatures that we've been experiencing. Well, then 2007 came along, then 2012 came along. So here was that trajectory of how the summer ice has been declining. This doesn't go down to zero. Zero's down at about here. But since this 1979 record began, here was 2005. Here, which was quite a low year for the time. 2007, it dropped off the table. Okay, it bounces back up a little bit. 2012, dropped off the table again. Now, last 2 years have been a little bit higher. So there's a lot of variation that depends on how stable the air is and lots of other things. But so now, on average, we're getting to the point where we're about 50% reduction in summer. So that report used to talk about the North Pole melting in sort of 100 years, 200 years. Well, now it's very likely that we'll be ice-free at the North Pole in your lifetimes. Maybe my lifetime. All right, so that's pretty strong evidence. You know, we're in the middle of melting the North Pole. There's another set of evidence, maybe perhaps closer to home here. And this is a different kind of record. These are USGS records of stream flow gauges and streams out west. So what do these data say? Well, when the snow melts, as I don't have to tell you here, you get this flush of water with the snow melt. And the USGS gauges track that peak on the hydrograph of flow as that water melts and the water comes through the river. And these are just different observations in different rivers and streams around the western US about the timing of melting from going back, I think, about 40 years or so. I can't remember the exact time scale on this. Deep red is 20 days earlier. than at the beginning of the record, and then the blues are later in a sense. So what you see is that the graph is overwhelmingly red, and in general in the western U.S., as in elsewhere around the world, in many places, the streams, the ice melts are providing information for us too. The snow's melting off earlier. That's even more important if you live in a state like I do in California, because we go 6 months without rain. And if the snow melts earlier, then we have to store even more water to maintain water for our reservoirs in our cities. Well, let's look at now at emissions. So we're sort of, like I said, this isn't a climate change discussion or seminar. Go ahead, sure.
Let me ask questions too.
Yeah, please.
Just going back to the last slide, I remember National Geographic ran a story last year, had this image of like the Statue of Liberty, like water up to its knees. And these sort of horrifying images of like all of the East Coast like being drowned. At the rate it's going, when could or would that happen? Sort of apocalyptic drown.
Well, so the short answer is no one knows, and I certainly don't know. I don't study sea melt and such. But if you read the literature and such, it depends clearly on how quickly temperatures rise, obviously, but then also how sort of incremental the ice melt is and where thresholds might be in that ice melt. And we have some ice specialists. Where's Summer in the room? We have some ice specialists right here. So I don't know how you would answer that question, but it's true, right? It's not necessarily just a sort of incremental decline.
Right. No, one of the biggest concerns being west of Arctic ice sheet, which is grounded below sea level, so potentially unstable. When sea level rises and chews away at it, it's one of the biggest uncertainties with potentially fast release of water into the ocean, but those are highly uncertain, so the rate is highly uncertain.
But let me add one other thing that may be partly the context for your question too. It isn't the case that melting of the North Pole contributes to that sea level rise, of course. That North Pole is like an ice cube floating in your glass of Coke. So its buoyancy is already incorporated into the sea level rise. But the Greenland ice sheet, is 10 or tens of feet globally of water, and Antarctica is a couple hundred feet. So people try and use the paleo record to explore that. So you're not going to see that kind of catastrophic sea level rise in your lifetime, I think the data suggests. But the sea level rise is increasing. And also you have to think about sort of that incremental or storm surges. There's pretty good evidence that a storm like Sandy that caused so much damage caused more damage because of the sea level rise that has already happened, right? So you get that surge on top of where the oceans are. So it's not just the sort of the long-term rise of the sea level, it's also the storms that happen and the surges. So let's talk about emissions. This is the kind of thing, these are Global Carbon Project graphics. This is the kind of thing we do. So what you're looking at here, we're going to go backwards. We're going to look kind of in the past at emissions. We'll look at emissions today, and then we'll do some projections looking at emissions into the future. Here's a figure where you're looking at the carbon dioxide emissions going back to about 1870 on the left, out to today on the right. Anything above this line is a source to the atmosphere, and the gray is fossil fuel use and cement production. This is the land use term. This is deforestation in the Amazon, or deforestation in the past in the United States or Europe or other places. Okay, and then down here you have the fate of that carbon dioxide. Where does it go? So if it stays in the atmosphere, it's here in light blue. If it goes into the oceans, it's blue here. And if it goes back into land because of land's recovering from past deforestation and such, it goes into this land sink term. So you see a couple things here. You see that in the past, the CO2 budget was dominated by human land use changes, whereas today, it's dominated far and away by the fossil fuel term. You see also that the land use term is getting better. Right? Deforestation is slowing, which is a good thing, the result of policies around the world. It's not zero, but it's smaller than it was 10, 20, 30 years ago. Okay, here's interesting too, because only about half the greenhouse gas emissions that we give off stay in the atmosphere. Right? So we were already sort of we're getting the oceans and the land sink that takes up about half the CO2 for us. So some interesting areas of research are to what extent will this continue? You know, at what point might our forests and other lands not be able to continue to soak up some of that extra carbon dioxide, and why might that be? Or in what ways might things like nitrogen deposition and fertilization and such mean that that sink continues? In the oceans, it's more of a physical process than a biological process through photosynthesis. But you know, the ocean sink is a little steadier than the land sink. You see the land sink bounces around, and that's because of bad wildfire years and you know, and things like that. So anyway, that's sort of the history of emissions. And this is just a summary of kind of those things in numbers. You have the emissions on the left, fossil fuel here, the actual numbers for the net emissions from deforestation, and then 44% stays in the atmosphere, almost 30% of the CO2 goes on land, and about a quarter of it goes into the ocean. Mm-hmm.
On that last slide, on the chart, there's a weird spike on almost every part of the graph on like 1995. So do you want to events cause that to happen?
Some of the biggest spikes are El Nino related. Can't remember the exact year, the year, for instance, of the really large peat fires in Indonesia and such. Those are the kinds of you know, really large-scale events that show up on that kind of those kind of graphs. Okay, let's keep going. Okay, this is a simpler figure. This is just the fossil fuel and cement emissions now, going from 1990 to 2014. So you can think of this as the period of time where we've been talking seriously about climate agreements, for example, you know, international agreements to reduce emissions and such. So you see that over this interval, emissions have gone up globally about almost 70% now during this interval. So in the decade of sort of the first half of the part of the 2000s, they were going up at about 3% a year. You know, over the last 6 or 7 years, they've slowed to about 2 to 2.5% a year, but it's still going up really pretty quickly. I mean, 3% a year is a doubling in, you know, what would that be? Less than 25 years, right? And then here's the projected value for 2014. The numbers are still coming in. And now we're up to about 37 gigatons of CO2 emissions a year from fossil fuels. All right, where is it coming from? Now it gets, I think, a little more interesting, a little more political or geopolitical. So here's a 50-year record of emissions for different countries. The US, China, the European Union, and India. So this graph doesn't represent the whole globe, but just those sort of 4 groups. You see the steady decline in the EU. That's partly a result of everything from economic declines to efficiency programs. You see sort of a tapering off and some slight declines here in the US. You see India increasing, and of course you can't miss what China's done over the past decade in particular. Right, so this kind of thing, these are the kind of data with which we need to grapple when we think about international deals and international trade and the next protocol. All right, so a lot of the action is clearly what's happening in China. Now, if you're thinking, you might say, well, that's true, that increase in China, but how much of those emissions are for products that we buy? So to what extent do we outsource or send our pollution offshore by buying products that were made in China instead of products that would have been made in the United States? To what extent does Europe do that? So that's what this kind of graph shows you. This would be work by Glenn Peters. Steve Davis does this kind of work as well. So this shows you the sort of the net import, not the net, but the import, if you will, of Chinese products in their embedded emissions in that trade. We export as well, so we have some that go the other way, net back and forth to Europe, some from Russia. Right, so how much do those numbers affect things? Well, they affect things a little bit, but they don't change the story fundamentally. Well, here's a similar graph to the emissions I showed you 2 slides ago. CO2 emissions again on the left, 1990 to current day on the bottom axis. India, EU, US, and China. And now the production emissions, if you will, just the physical, literal emissions within the country are the solid lines. And here's what their emissions are if you include the things that they use nationally, internally. Or put differently, these are the net emissions that go to products that they export to other countries. So that's why our numbers are actually higher, in this framework at least, than the production emissions, because we're a net importer of goods from elsewhere around the world. But so it changes things sort of 10 to 15%, if you will, but it's not a deal breaker in terms of the overall picture. And these numbers are a little fuzzy. You have to make some estimates about the embedded emissions in different products, computers and televisions and food and lots of other things.
The president of China, I mean, for not being interested in his name, and President Obama just made an agreement about reducing their emissions to certain levels. Can you tell us a little bit about that agreement and if it will help or if it's going to be effective or not?
Yeah, so there was there are other people here who know a lot about it. I just know the very general framework. China announced, this was a month or two ago, at the recent climate summit, and China announced that I believe they would cap their CO2 emissions by 2130. I think that's the date. Does anybody else know that exactly? I think that's correct. So they said our CO2 emissions will increase, but they will top off in the year 2130, in about 15 years. And then 2030, excuse me, yes. Did I say, yeah, I just said 2130, 2030. So in about 15 years. And then I don't remember the specifics of our commitment, but it was a continuing, fairly modest decline in US emissions too. And that's, a lot of things have to happen for that to come to fruition. But important in the sense that the first time that China in particular has made a specific comment about what they'll try and do with their trajectories. Okay, so one framework. So I guess what I want to spend the few minutes we have left thinking about different frameworks that you can apply to these emissions, and thinking about what an agreement might look like, and what metric do you use to decide how many emissions a different country is allowed to emit, if there's any kind of agreement in place. So here's a different framework. That's an obvious one you've all thought about, and that's per capita emissions. Right, so emissions per person. Yes, China is now the world's largest emitter, but China has 4 times roughly the population that we have in the United States. So the per capita for the United States is up here, about 16.4 tons of CO2 per person. China's about half that. Europe's about half that too. Here's the world average, and here's India. Right, so one of the really remarkable things is now that Chinese consumption is equal to or slightly greater than the European consumption on a per capita basis. I mean, that's pretty remarkable. And China has very much a dual population. You have rural people who are not using much fossil fuels at all, and then you have urban populations that are now emitting, now using resources in the same way that we do. Okay, so we're still the peak in terms of per capita emissions, but then India is way down here. Right, so when India talks about India just signed a 100-year agreement, I believe, with Australia to provide coal, for Australia to provide coal to India. So they have a guaranteed source of energy. And I think countries like that can say with some justification that they have a responsibility to provide energy to their population. Millions of people which don't even have electricity yet. The per capita emissions is another framework that people use to evaluate these kinds of numbers. But it's not the only framework. Right, so another one is cumulative emissions. So here are the production emissions today. If you just took 1 year, so here's our, roughly 50% of emissions today come from the European Union and the US. So we have other countries. This is let me back up. This is a cumulative graph, percentage of emissions through time. And what this shows you that if you were to look back in time, say at 1880, most of the carbon dioxide that was in the atmosphere came from the United States or the European Union, almost 100% of it. If you look today, China is responsible for about 10% of all the CO2 in the atmosphere. So a different way of looking at it is the atmosphere is a bucket. Now we can fill the atmospheric bucket with so many billion tons of greenhouse gas pollution. And then at some point we have to stop. And some countries can correctly point to that bucket and say, well, I may have higher emissions today, as in the case of China, but most of the junk that's in the atmosphere is yours, not mine. Right? So some countries advocate a cumulative approach for applying future emissions. How much emissions will I get to have in the future? Well, it should not just be about what we use today. It ought to be about everything that's here in this bucket. Or it ought to be about per capita emissions. So these are the issues that policymakers are grappling with and trying to, when you're trying to reach agreements on these things, it's complicated. And here are some, here's just a simple graph that shows the different perspectives that those things provide. So here's what it looks like on cumulative emissions. China has about 10%, we've got about 25%, Europe's got about 20%, then the other countries are up here. India's still really small. India's got over a billion people, and they're still really small in all of these metrics. Production emissions, China's the biggest one today. Okay? Here's a production basis. China's a little smaller on the consumption basis. Here's just for purposes of comparison, the population graph. All right, so it's an area that there's a lot of thought. There are issues of equity embedded in it, equity, history, and clearly economics, and even the environment. And then finally, we can think about that bucket. Let's look at that bucket in the atmosphere. How much greenhouse gas can go into that bucket and remain under safe levels? How do we know? What's safe? And who gets to add the remaining carbon dioxide? So here's an estimate from a bunch of models for the Earth, part of the IPCC assessment. So here's the best guess for how much CO2 we can have in the atmosphere, and methane and other gases too. They all count. But it's mostly about carbon dioxide. Here's what we can have to keep the Earth within about a 2 degrees C peak warming. So that would be about 3.5 degrees Fahrenheit. Right? So this is there's some error about this, like this, but the models, these are what the Earth system models suggest the greenhouse gas budget shouldn't go above unless you want temperatures to rise more than about 3 or 4 degrees globally. Okay, here's where we are, 2014. And then zeros down here again. So we've loaded the bucket with this much. We've got this much left. And depending on how much these emissions rise, and they are still continuing to rise, we get to this point within about 20 or 30 years. Okay, so we don't have very long, is the point of a figure like this. Now there's nothing magical about 2 degrees. The world doesn't stop turning at 2 degrees. But there's pretty robust sets of evidence that say important things start to happen to our water, to our air, to our ecosystems, to our ice, to sea level rise. But of course, if it goes to 3 degrees C or 5 degrees C, it's worse. Right? But if you let it go to 3 degrees C or you let it go to 5 degrees C, you get a bigger bucket to play with. Right? So that's what we've got left. And I think the point of this slide for me is just how close we are to that 2 degree threshold. Think about how old and how long lasting most of our infrastructure is. Take our energy infrastructure. And we build a coal plant. That coal plant operates for decades. And we build a natural gas plant. So the decisions that we make today about everything from our electricity to our transportation have decadal scale effects. So there are about half of this, I think the number is right, about half of this, what's left, is already sort of embedded in the infrastructure we have on place on Earth today. It's already been built. And then finally, we'll end the emissions part. This gives you a different take on the cumulative CO2 emissions around the world by year, just from their sources. Here's the land use term. Here's coal. Here's oil, gas, and other sources. So historically, it was mostly about coal. Today, it's still mostly about coal, but oil is a large part, and gas is growing very, very rapidly.
What's the spike? 95, 97?
Here?
Yeah.
I don't know. That would be, I don't know is the short answer. It looks like it's right before the crash too. That may be, this may be wrong, but that may be right when the economy was sort of at the peak before the 1999, 2000 downturn. I don't know what that is. Does anybody else know?
No, but I just have a question.
Mm-hmm.
How do you see that graph changing going into the future with India and China developing? Do you think coal will power? I mean, you said something about Australia powering India with coal for 100 years.
Well, they signed a contract, or at least an agreement has been signed for Australia to supply coal to India. I think it depends where you are around the world. In the U.S., the proportion of coal that we use for electricity and manufacturing and such has been dropping, whereas the consumption of natural gas has been increasing. I think you'll see the amounts of natural gas in particular go up globally. You'll probably see oil come down a bit because it's more expensive, and you'll see parts of the world, India in particular, and China is building coal facilities very rapidly. So I don't think you'll see the coal decrease too quickly, but you'll see it decrease here, and it's already decreasing in places in Europe and elsewhere. So, but I think another aspect of this to me is just that we can't turn on a dime. You know, this all our manufacturing infrastructure, our energy infrastructure, we just can't switch it on and off. It takes tens of years to really turn these kinds of curves around. And every year we don't do anything, we just sort of increase the bucket. Mm-hmm.
Do we know, is there plenty of coal, oil, and gas to fuel us into that 5 degree C range if we choose to?
There is enough coal, oil, and gas to fuel us well beyond 5 degrees range. That's coal in particular. And one of the most, one of the biggest changes that you're all familiar with, and it's what I talked about this morning, was just how much oil and natural gas reserves have increased over the past decade because of the technological advances of hydraulic fracturing. I mean, there's much more economically accessible natural gas and oil now than there was 10 or 15 years ago. But there's boatloads of coal around the world. So at some point, I'm an environmental scientist, I'm not an economist, and I'm not a president, but at some point, we got to stop using it or find other technologies to take it back out of the atmosphere, because there's more than enough to cook the planet with. Sort of a, when do we start the diet? And in some places, the diet has already started. All right, this is a shale gas analogy just to continue that idea. I showed this slide this morning, but these are the, these aren't new sources, of course, because these have always provided some of the oil and gas that we've mined elsewhere, but these are where people are going for the shale oil and shale gas, and other unconventional sources of oil and gas aren't even shown on this, like tight sandstones and such. So there is a lot of new oil and natural gas that can be exploited with hydraulic fracturing in countries like China, South America, Latin America, Argentina. So we're not going to run out of fossil fuels in this interval. Okay, this is just one or two more figures and we'll stop. These are the different pathways, if you will. So these are called representative concentration pathways, and this is what has to happen to emissions, for instance, to stay down at about 2 degrees, 3 degrees, 4 degrees, and even higher. And here's where we are. So back in 1980, 1990, there were these different scenarios envisioned, and this is the track that our emissions are on right now. So this just is another way of illustrating that we're leaving these lower trajectories behind, and right now we're on a sort of 4 or 5 degree C trajectory. Mm-hmm.
You had mentioned that there would be like some really negative effects, like the air, the water, or land, if we do reach that point in however many years. Could you like elaborate maybe on some of those, or is that like something that you research?
Well, the most obvious are things like the ice melt, sea level rise, drought, extreme events for weather, droughts, storms, increased large, potentially hurricanes. There's good evidence to date that we're seeing an increase in large-scale droughts. There's not good evidence, I believe, to suggest that we're seeing more hurricanes to date, but I'm not a hurricane specialist. But those kinds of things. So this is just another way of showing that we're on a trajectory that's speeding past. We're leaving behind some of the options that we had even 10 or 20 years ago. And I'll finish, I mean, just a couple of other things you're starting to hear about because of the lack of action on greenhouse gas emissions. Policymakers now are starting to think about really kind of science fiction-y sort of things, like geoengineering. Geoengineering is the possibility of mimicking volcanoes. If we were to blast dust up into the stratosphere, we could block sunlight to cool the earth a little bit. And you don't have to blast a lot of it up there. You just have to get a little bit up there to make a difference. All right, so climate planetary control, if you will. And we could talk about how you might get that done in the United Nations. As a sideline, we can blast dust into the stratosphere. But you can't change the stratosphere temperature budget through dust without altering rainfall. And this kind of process tends to reduce rainfall because you're reducing the sunlight that reaches. So, you know, it's like the Wizard of Oz. You know, we start twirling more and more of these knobs to try and keep things the same. But you'll start to hear more about this. So finally, I'll finish just with this, that you know, regardless of your particular opinions or whatever, that by tackling global warming, we can do a lot of other good things. Address global warming and we improve our air quality and save lives. Renewables reduce water use. So in the US, coal-fired power and car exhaust are the sources of the big 6 pollutants that the EPA regulates and that kill people. All right? This was an interesting sort of story. In 2003, was anybody in the Northeast when that big blackout occurred? Well, this was the period of time when the Northeast went dark, when the power grid failed. Right? When the power grid failed, the visibility improved by 25 miles. Smog and ozone pollution dropped by half within a day, and gases contributing to haze and acid rain dropped 90%. But that's the consequence, particularly of our coal-fired energy infrastructure. And then finally, urban ozone formation, as another example, is highly correlated with temperature. As temperatures go up, extreme hot summer temperatures lead to extreme ozone days. So all of the suite of things and many, many others can be addressed through a thoughtful energy policy. And I hope we'll get there. Thank you.